Okay, so here are the class notes for section 8.1. Sorry I can't be with you there today, but wanted to make sure that you got a good understanding of this before you do your little lab activity, which unfortunately will also be a video for you. But we're going to just go through some of the key concepts in 8.1. Hopefully, through the reading this section, you have associated the word covalent to sharing electrons. So we talked about giving and taking electrons back in chapter 7. Covalent is sharing electrons, forming molecules. So covalent compounds, molecules, molecular compounds, all of those, they all mean the same. Sharing electrons between atoms to become stable, okay? So monatomic means one atom, and there are elements that exist as single atoms because they're already stable, and hopefully that rings a bell to you. The ones that are already stable are going to be the noble gases. So those are our monatomic elements, okay? Then we get into molecules. Diatomic molecule, hopefully you have this part in blue here, it's a molecule that contains two atoms because di means two, atomic is atoms, okay, diatomic. The elements for diatomic atoms are going to be all of the gens is one way to remember it. Brinkelhoff is another way to remember it. Or you could say the gens and the enes, so anything that ends in G-E-N or I-N-E. So we've got hydrogen, nitrogen, oxygen, those are our gens, okay? And also the halogens, which is group 17, and all of those elements end in INE. So we've got fluorine, chlorine, bromine, iodine, okay? Technically acetine, but that we're not going to be finding or working with that. That one's pretty rare. Okay, so all the enes and the gens is one way to memorize this, which you should do, memorize it, okay? Or all the gens, or Brinkelhoff, because if you put their symbols together, B-R-I-N-C-L-H-O-F, you get Brinkelhoff, okay? But all of these, I'm going to just go ahead and write Brinkelhoff. All of those, when they are in their pure form, they're going to be diatomic, so two atoms sharing electrons to be stable. So Br2 would be bromine, Cl2 chlorine, O2 is oxygen, which some of us are already familiar with that. Okay, now we're going to get into molecular compounds. Okay, now molecular compounds, the definition in the book is a compound composed of molecules, which means they're sharing electrons in order to be stable. Okay, and we're going to just talk about the types of elements real quick. When we were looking at metals with nonmetals, that was ionic because we're giving and taking. When we look at metals with metals, they're not forming covalent bonds or ionic bonds, they're forming mixtures called alloys. And that was the end of chapter 7. Now we're looking at nonmetals with nonmetals. So types of elements, in that you just have to write nonmetals. So two nonmetals together in a compound or three nonmetals together in a compound, those are always going to be sharing electrons, and that's going to be a molecular compound or a covalent compound. Okay? All right, molecular formula. Existence of a molecular formula. We talked about ionic compounds as not existing as individual units. Those formula units do not exist by themselves, okay? But molecular formulas, they do exist as individual units, okay? They are molecules. So these do exist as individual units. These do exist as individual units. So you will find H2O, one oxygen with two hydrogens attached to it, floating around by itself in nature. Because it's stable that way, we don't have massive charges on that molecule that are going to cause it to stick to things around it like we do with ions. Okay? Okay, moving on. Molecular formula shows how many atoms of each element a substance contains. Okay, and we're going to just compare covalent formulas and molecular formulas for a second. So covalent formulas show the actual number of atoms in a molecule, okay? So covalent formulas show the actual number of atoms in a molecule. Actual number of atoms in a molecule. So that chunk, that unit does exist, okay? Versus ionic formulas are not showing the number of ions, because in order to get a tiny little crystal of salt, we'd have to have billions and billions and billions of ions. And so we're not going to write Na 15 billion, Cl 15 billion. We're not going to do that. We just write the ratio. So ionic formulas show a ratio in a crystal, are always reduced to the lowest ratio and represent the ratio in a crystal, okay? So always reduced to a lowest ratio of ions in a crystal. Always reduced to a lowest ratio of ions in a crystal. And remember, that's going to be based on their charges. If they have the same charge, that ratio will be 1 to 1. If it's a 2 plus and a 1 minus, the ratio is going to be a 1 to 2 in order to balance out those charges. Okay? So skipping down a little bit, we've got the representative unit for a molecular compound. It's a molecule. For an ionic compound, it's a formula unit, which you know how to abbreviate. It's Fu. Okay? Now, differences in what those represent. Again, this is kind of repetitive, but it's going to help you remember. Okay? So, molecules, again, these are covalent. Okay? Those represent covalent compounds, and they are individual units. They are individual units. They do exist by themselves. Okay, ionic compounds, we have formula units. For ionic, formula units, ionic, do not exist individually. Do not exist individually, okay? They exist in that ratio in a crystal that is a repetitive pattern of billions and billions of ions in order to find a tiny, tiny little grain of that compound, okay? Okay, the final piece on that page is properties of molecular compounds in relation to ionic compounds. In the book, you should have gotten molecular compounds tend to have relatively lower melting points and boiling points compared to ionic compounds, okay? And that was just one of the 3 properties that we talked about with ionic compounds. Ionic compounds are solids at room temperature. Ionic compounds have very high melting points because, again, we have to break bonds to melt them. And ionic compounds are conductive when in liquid form, so dissolved or melted, okay? But for some reason, the book only talked about the melting and boiling points for covalent compounds being low, okay? They're lower than ionic compounds. So if you could, at the bottom of your page there, add into that box of properties. We're going to talk about everything else. So physical states is the first thing that we talked about for ionic compounds. And physical states for covalent can be solid, liquid, or gas. It depends on the compound. They could be any of them, okay? In general, if they're solid, they're going to have lower melting points than ionic compounds, but the liquids and gases, they're already melted or even boiled at room temperature, okay? So they have very low melting points. All right, the other thing that we talked about was conductivity. Remember, ionic compounds conduct as liquids because their ions can move, and ions are charged particles. Metals conduct electricity because their electrons can move, and electrons are charged particles, okay? Molecular compounds are not conductive. Not conductive, okay? A molecule is neutral. When you dissolve sugar, for example, the sugar molecules all separate, but they are still molecules, and molecules are neutral. So even though they can move, they're not carrying a charge around the system. That is not conductive, okay? So water is not conductive if it doesn't have ions in it. Now again, anything's conductive if it gets struck by lightning. But when we're just talking about water, pure water, it should not carry a current because there are no charged particles in it, okay? So hopefully that little overview will give you enough information in order to do your lab today. Thanks.